I would like to begin with a quote by Felix Klein. So we all know who Felix Klein is. That is the guy who got named after the bottle. Everyone knows what a curve is, unless one studied much mathematics. Not the exact quote, but I'm paraphrasing. And basically, what Felix Klein was trying to say is, what exactly do we mean by a curve in mathematics? And then we can ask questions about curves that you would think are fairly straightforward, but they can get very bizarre. So let's just focus on this, like what exactly do we mean by a curve? And there's actually many different definitions. Depending on the context. So depending on what you're doing. So sometimes you have to vary the definitions. So for instance, we could say that a curve in some space x is a function, is a mapping from the interval into x. But then you have to realize that then a curve is a mapping and not the set. It's not the image of it. Because, so what that would mean is that, so if you have two different mappings, we could have that f and g are different mappings, but they have the same image. So we would say we have two different curves, even though that might sound somewhat confusing because they trace out the exact same image, but we do that often. Actually, a lot of the times when we work with, let's say, the fundamental group, we can have two different curves, and we can say there's a homotopy between them. So even if the images are different, we still might say that they're somewhat the same. But that's one way of defining a curve. Then we also talked about one chains. So a one chain in X intuitively is supposed to represent a curve, but a one chain is a formal sum of these paths, of these mappings. So it's a formal sum, A1, F1. So you can repeat them, you can orient them, and so on. And when we talk about a one chain, we do the same kind of phenomenon where we can have two different mappings. They trace out the same kind of image, but we call them different nonetheless. Now, a lot of the times, if two different mappings trace out the same image, then often they would be probably homologous. Often, not always, but often that's what's going to happen. So you do have some way of identifying two chains as being the same, and then in that sense, one might say that they're sort of equivalent, even though they might be formally different. So that's another type of definition that comes up. Then we also talked about graphs. So we talked about X is a topological graph. And then intuitively, that just means it's like different pieces perhaps coming together in some kind of way underneath, whatever. You might say that this is a curve, or maybe pieces of curves, but you might say this is a curve. Now this one's a little bit different because there's no mappings anymore. This is now a topological space. So when you talk about graphs, you're not talking about mappings anymore. You're just talking about a topological space with a triangulation property. So as you can see, what we mean by a curve is a bit ambiguous. Also, to make matters even more complicated, there is a curve in algebraic geometry. This is the most difficult concept of a curve. This one uses a lot of algebra, in fact. There's less topology and much more algebra. So there's a notion of a curve. And in algebraic geometry, one would say something like a curve over, and then you write the field that you're working over. So you might say a curve over the complex numbers. And as a topological space, it is two-dimensional. So it is a surface. So basically we're saying a curve in algebraic geometry is a surface if you work over the complex numbers, because the idea is a single complex variable is two-dimensional. So that's kind of funny that it becomes a surface. But it gets even more complicated because it depends what kind of topology one is using on the curve. So usually one uses a different type of topology called the Zariski topology, whatever that means, in which case it's no longer a surface. So it becomes complex. It becomes fairly complicated. So that just nicely fits with what Felix Klein said. And furthermore, curves, I'm going to put a curve in quotation mark because we're not going to define what a curve is, because there's not really one definition. It's just depending on what you're doing. Curves often have pathological properties. So, for example, there's something called a space-filling curve. And the first person to give an example of this was Peano. So it's a function from 0, 1 into, let's say, R2, so that the image of that interval is the unit square, as bizarre as that might be, which completely breaks all intuition. This is supposed to be one-dimensional. This is two-dimensional. So how can it possibly be that it gives you a square? And there's even explicit constructions for such functions. So it's not even like one of those theorems in math where you just assert that something is true and you never provide any examples. But there's actually explicit examples of that. So if you have, you can find an example. So if you look at Topology by Moncrief, he actually shows you an explicit example of something like that. So Peano illustrated that you can have a function that is continuous and its image completely breaks all intuition. Now, as we've said this before, this is like a common theme in mathematics. If you replace the word continuous by, let's say, differential, so I'll just say smooth, then this is not going to happen. Then what's going to happen is the image as a subset of R2 would have what we call measure 0. So it cannot possibly be the unit square. Now, if you have no idea what that means, just ignore that. You do not need to know it. But if you know what that means, you can see that by adding the assumption of smoothness, it does not actually have to be infinitely differentiable. But I just written it like this. So if you add this assumption, then things, it tends to work out in the way you expect it to, right? It's something, the image is something that when you measure it in a two-dimensional sense, you're only getting a one-dimensional object or smaller. And then this agrees with the intuition. And proving this is actually not hard whatsoever. It's because you have derivatives, you can estimate how big they get, and then you apply the mean value theorem on the components, and that's how you can cover that by arbitrarily small rectangles. So that's why it's measure 0. But if you have no idea what I just said, you can just ignore that. But that's like a common situation in math. By adding smoothness, things become more aligned with your intuition, whereas continuity is often pathological. Now, the next thing that I wanted to say is, okay, yeah, so this is what we call like a space-filling curve. And I'm going to give you some other examples. So in a moment, I'll give you another example of a somewhat pathological type of curve. But I first want to make a definition. Let me start with this definition. So definition, C subset of R2 is a Jordan curve, or you can say a simple closed curve. So notice here, we're no longer talking about a mapping, but the definition will assume a mapping. If and only if there is a continuous map, F. And instead of making go from 0 to 1, because when you talk about a closed curve, you put the endpoints together, I think it's just easier to talk about a circle. There's a continuous map from the circle into R2. so that the image of the circle is C, and F from S1 to the circle is a homeomorphism. So basically, it's a subset of R2 that is homeomorphic to a circle. That's what we call a Jordan curve. And basically, this is R2, and then the Jordan curve it can be very complicated. I mean, it could get so complicated, in fact, that it resembles a little bit like a space filling curve. You can have some kind of fractal or something. You can have some kind of fractal. Maybe it kind of goes up and down like this, sort of like the topologist sine curve or whatever. It can sort of get thicker over here. It sort of fills out like a fractal type of shape, but it still satisfies this condition, but it could be fairly complicated. It's still homeomorphic to the circle. So it's something that's homeomorphic with the circle. And that's what we call a Jordan curve. And despite curves being pathological, all Jordan curves in the plane have an inside and an outside. No matter how you draw a Jordan curve, there will always be an inside and there will always be an outside. Now, how do we define inside and outside? So the way you define it is you look at the complement of the curve. And when you look at the complement of the curve, you have two connected components, two path components. And that's what the Jordan closed curve theorem says, that despite curves being so pathological, and even though these Jordan curves can be even space filling, despite that unusual behavior, there's one nice property that they always share. And they always have an inside and an outside, which at first it sounds obvious, but then you realize how strange curves can be. And then it's actually a pretty impressive theorem that no matter how you do it, there is always going to be an inside and an outside. So the theorem says that if C is a subset of R2 is a Jordan curve, then R2 take away C has two path components. Two path components. You can also say connected components. In this case, path component and connected component is the same thing, but let's not even go there. It has two path components, and you call one of them the inside and the outside. And if you wonder which one is which, it's very simple. The outside, that's the one that is unbounded, right? The one that's not bounded. So that's the Jordan curve theorem. And the history of this theorem is people tried to prove this theorem for a long time unsuccessfully. And you will see why, because you have to use algebraic topology to do that. And because they were unable to prove the theorem, and because they knew that curves can be very bizarre, they tried to produce counterexamples. But no one was able to do it because it turns out being true. So that's what we're going to talk about. How one proves a theorem like this. Now, I want to, before we get to the proof of this, I want to make another definition. Here's going to be a definition. We're going to say that A subset of R2 is a Jordan arc if and only if. So I'm just going to say this, that A is homeomorphic with the interval. I mean, I could say that there's a homeomorphism from the interval to A, and I guess I should have done that with the Jordan curve also. I mean, we do not really care so much about the map, but that there is a homeomorphism. We do not care what the homeomorphism is. We just care that there is one. So it's homeomorphic with the interval, and we call that a Jordan arc. And just to give you some pathological examples, so here is a pathological example of a Jordan arc in R3. So you would guess that if you look at its complement in R3, that it should be simply connected. Okay, so why would you guess that? Well, let's say this box represents R3. And inside the box, you're going to draw a Jordan arc, right? So some kind of arc in the box. So you're claiming that the complement is simply connected. So this will mean that if you have a loop, a closed loop that avoids the blue arc, then you can shrink it to a point. Well, because it does not touch it here, you can clearly shrink it down to a point. But what if this loop, it like winds around that arc? Well, that's not a problem because the arc has open ends. You can just take the loop, you can just slide it over and keep on sliding it over until you escape. And then after you escape, then you can just shrink it down to a point. Now, you can have a more complicated type of arc that, let's say, the arc kind of goes like this. It goes through itself, and then it kind of goes inside it. It goes over itself like this. But you're not allowed to close the ends. It's not an actual knot. And then you may worry, and then you may say, well, what if I have, let's say, a loop that kind of goes through it or something in some kind of complicated way? Can I shrink that loop to a point? And if you think about it, the ends are open, right? These ends are open. Doesn't matter. You just take, if there's a lot of tangling going on over here, you can just take like one of those like threads and just push it around and push the other one around. And you just keep on doing it until you can just untangle the whole thing because the ends are open. And then you're left with a loop. You move the loop completely outside this arc, and then you have room to shrink it down to a point. So that's what you would think. It just makes sense. And this is the part which is quite shocking, that this just goes back to curves do not necessarily behave how you think they do. So there is something called, you could live in Bredin. So Bredin draws a picture of this. He gives an example of something called the Artin-Fox-Wild arc. There's also something called the Artin-Fox-Wild knot, and this is sort of the same, similar theme. And basically what it is that A is a Jordan arc. A is sitting inside R3, but the complement is not simply connected. Once you see the picture, it would be maybe believable to you why that is, but it's just what we say, curves are very pathological. So, and you can see that because it behaves so pathologically in R3, maybe the Jordan closed curve theorem is not true. Maybe there is something so bizarre like that. So that's why it feels obvious, but when you see all of these strange examples, you realize one has to be very careful with making that claim. Okay, so let me just remove this. So that's why we call a Jordan arc. And now we're going to have a lemma. And the lemma will say that if A is a Jordan arc, then the complement R2 take away A. So this is kind of like the Jordan closed curve theorem, where you're looking at the complement of the closed curve. But this is not a closed curve. This is an arc. R2 take away A is connected. So it's by connected, we mean path connected, which is the same thing as connected in this case. So it is connected. So that's going to be a lemma, and we're going to begin by proving this lemma. I guess I should have said one more thing that I forgot. Let me just make this, I should say this. The Jordan closed curve theorem is easy to prove if we assume that this homeomorphism from S1 to the Jordan curve that's sitting inside R2 is smooth. The reason for this is because differentiable basically means linear, right? When you take like an advanced calculus course, they say that a lot, that if something is differentiable, it means it can be approximated by a linear map reasonably well. And so what this would mean, this is kind of like an outline, is that if you have your Jordan curve and it can be described by a smooth mapping, then by taking like subdivisions, like if you subdivide the interval, then you can approximate it by a straight line so that it's sufficiently close with the curve. And then what you're getting, and if you look at what you're getting, then you're getting a polygon. You end up getting a polygon. And you then prove the Jordan closed curve theorem with the assumption that you have a polygon. So a polygon would just mean it's a Jordan curve that can be expressed as a finite union of line segments. So in that case, there are elementary proofs of this, that you can look into. But our proof will include that proof as well. And often that's what mathematicians did in the past, that before they knew the Jordan closed curve theorem, sometimes they realized that knowing that you have a polygon, that it's true for polygons, is sufficiently good enough for what they were doing. So that's going to be a lemma. And I should have said one more thing before we talk about the proof of the lemma and then the Jordan closed curve theorem. You can ask, is the Jordan closed curve theorem used for anything other than being interesting? So is it basically like Fermat's last theorem? Like Fermat's last theorem, even though it's a nice theorem, I think we can all admit it's not used for anything whatsoever other than being an interesting problem. The benefit of Fermat's last theorem is it led to the development of an enormous amount of mathematics that pushed math much further than it ever was before, which would have not been possible without Fermat's last theorem. But the theorem in and of itself is not used for anything. So you can say, is Jordan closed curve theorem like one of those problems in mathematics that it led to the creation of various topological ideas, which themselves are important, but the theorem in and of itself is not important. And actually, what we can say here is it is used in what is known as the triangulation theorem. So what's the triangulation theorem? It says that every two-dimensional compact manifold can be triangulated. So we talked about what a triangulation is. So a triangulation, so we said a topological space has a triangulation if there's these mappings of simplices that fit in a nice way. So we define what a triangulation is. And if you have a compact two-dimensional manifold, it has a triangulation. And you have to use the Jordan closed curve theorem to justify the existence of a triangulation. So that's kind of interesting how it comes up in such a way. So now let's discuss the lemma. So I'm going to remove this and we'll start doing some proofs. Before we prove anything, let's do a simplification. So we will embed R2 in S2. This is a common trick. So I'm sure you've seen this before, but if not, this is R2, and then you have the origin, and then you draw the unit sphere so that it passes, so that half of it passes through, is cut by the plane. And then the mapping from R2 to S2 is very simple. This is the North Pole, and if you have a point in R2, you just draw a line, and that line will intersect the sphere in a unique point, and that's how you map R2 onto, not onto, but into S2. And this is you can show it's a continuous map, and it's a homeomorphism onto the image and all of that stuff. But that's like the geometrical picture for how you're doing. Writing out the actual equations of that is fairly annoying, but the important point is that such an embedding exists. So why do I bring this up? Well, I bring this up because if you have, let's say, an arc in the plane, if you have an arc right over here, a Jordan arc, you can map that arc onto the sphere. And then you'll have the arc on the sphere. So you can convert, so instead of working with the plane, it's more convenient to work with the sphere. And it's not for the reasons that you think. Like you would think that, oh, it's because the sphere is compact, and that is not. That's actually not the reason why it's convenient to use the sphere. It has something to do with punctures. If you take a sphere and you make a hole in the sphere, it's still connected. But if you take R2 and you make a hole in it, well, it is still connected, but I meant to say was, if you take S2 and you make a hole, it's simply connected, whereas this is not simply connected. So it has to do with connect. Here we're more interested about how connected something is, and S2 is more connected in some sense than R2. In the sense of punctures, I should say. When you do punctures, S2 works better for connectivity than R2. So this is the way our lemma is going to go. We have a lemma So we're going to say that if A is a subset of S2 is a Jordan arc, then S2 take away A is connected, path connected. So we're just doing the same thing, but we're doing it on a sphere instead. And now we're going to give a proof of this. Proof. Let F be a map from 0, 1 into A that's sitting on S2 be a homeomorphism. We know a homeomorphism exists because that's the definition of a Jordan arc. The next thing that we do is we're going to let... Now, as we're writing this proof, I would like you to appreciate the fact that no pictures are going to be used. This is a completely rigorous proof. Like, there's nothing suspicious. There's no part of this proof that you're going to say that I'm not so convinced because I'm drawing a picture and making you believe that something should happen, but it's not completely rigorous. This is completely rigorous. So that's quite nice. This is a completely visual statement that's been reduced down to formal mathematics. And we're going to let A1, let's actually call it A prime. Let's say A prime is the image of the first half of the interval, and A double prime is the image of the second half of the interval. So we cut the interval in half. So then A prime and A double prime are Jordan arcs. But here I just want to say that their union is going to be A, right? Because the union of these two gives you A. And their intersection, if you were to intersect them, that would just be F evaluated at 1/2. Because F is a homeomorphism. It maps all of these points into different points. So they're all going to be different points. And the only one point they have in common is where they intersect there. And we're going to call that point P. And that's going to be some point on the sphere because all of these are subsets of the sphere. So this is the setup. The next thing that we're going to do is we're going to let U prime be S2 take away A prime, and U double prime be S2 take away A double prime. So these are open sets of S2 because A prime, A double prime, they're closed sets. The reason why they're closed sets, by the way, is because this is compact. The image is compact, so you have a compact subset of S2. S2 is Hausdorff closed. It's just not very interesting point set topology. So these are open subsets of S2. And now let's see what happens when you take the union, where the union of U and U double prime would be S2. Take away the point. Because when you take a union over a complement, that's a complement, it's the complement of the intersection. And the intersection is a point. And if you take the intersection, then that would be S2 take away. So the complement over an intersection is the complement of their union, and the union we said was A. So that's A. So this is sort of the setup. And now we can apply the Meyer-Vittoris sequence. So we're going to use homology here. So we're going to apply, so by the Meyer-Vittoris sequence, actually, before I write anything down, this is a very natural thing to do. One can argue that we're not exactly doing anything that's super clever over here, because if you want to show that something is connected, if you're using homology, you basically want to show that the zero homology of that complement is isomorphic to Z. If you're using homology, if you're using a homological approach, this is what you have to compute. And so it's very natural to do this. And so you were interested in computing homology, and we compute homology using Meyer-Vittoris sequence. Well, that's one of the methods. So we're using it right over here. And so it does make sense what we're doing. Like, it's not like out of it. There's actually, I want to maybe make just an interesting comment that we're not going to use. There is, I just found out about this. I did not know this. But there is a proof of the Jordan closed curve theorem by using Brouwer's fixed point theorem. very surprising. So we did talk about Brouwer's fixed point theorem before, and I said it has interesting appearances in mathematics. So it's quite interesting that you can use it to prove the closed curve theorem. Though I briefly looked at the paper that had it, it was somewhat long, and just by scanning it, it seemed to use some ad hoc tricks. And I'm the type of person that I prefer a more natural proof. Because if you're using an ad hoc type of a proof, you do not really understand why it is true on a deeper level. You just know it is true because you can prove it, but you do not really understand what is going on a deeper level. And when you have a more natural type of an argument, then you're getting it on a deeper level. So anyway, so we have a Meyer-Vitorla sequence, and this is going to be the part of the sequence that we're going to work with. We're going to look at S0. We're going to have U prime intersect U double prime. Then we have U0, I'm sorry, H0. We have U prime plus U double prime. And then you have that lowering of dimension map. So this is going to be H1. And this is going to be the union of these two. U1 union U double prime. U prime union U double prime. And by the way, if we want to replace these, this is of course what we're interested in. This is S2 take away A. This is S2 take away A prime, where A prime is the left arc. And this is S2 take away A double prime. That's the other half of the arc. And U union U double prime, we've said that this was S2 take away the point at which the two arcs meet. Okay? Now, here is what's going to be useful. So we want the first homology of the punctured sphere. Punctured sphere has first homology trivial because this is contractible. So this entire piece is just going to be 0. And that means that because we have an exact sequence, it means that this mapping is an injection. So we have an injection of this group into that group. Okay, so now we're going to do this by contradiction. So if S2 take away A is path connected, then we win. There's nothing else to be proven. The proof is complete, right? Otherwise, we can find 2 points. Let's call them x0 and x1 in S2 take away A, which are not path connected. So what I mean by that, of course, is you cannot find a path between them, right? There's no map. Okay, maybe I should write it out. A function from 0, 1 into this complement with f of 0 is x0 and f of 1 is x1, right? A path between them that lives inside S2 take away A. So if it is not path connected, means between any 2 points you can find a path. So if it is not path connected, then there's at least 2 points, at least 2, that for which there's no path. Now, we want to show it is path connected, but we're assuming, let's say it is not. Okay, so what do we get from here? So here's what's going to happen. We're going to pick, this map is injective. So that means, okay, so here's the main observation. So hence, x0 and x1 are in different homology classes. Maybe we should indicate 0 homology. Right now we're talking about 0 homology. 0 homology just is referring to points. X0 and x1 are in different 0 homology classes in S2 take away A. So I want to just remind you again that 0 chains are just points. In fact, a point is automatically a cycle. And 2 cycles of dimension 0, in other words, 2 points, are homologically equivalent if there's a path between them. So x0 and x1 are homologically different in this group. So let's write over here x0 and x1. So they are different, right? So they are not equivalent. Maybe I'll write it like this. They're not equivalent. Their homology classes are different. So now you have to recall how this map works. This is the diagonal map. The diagonal map is the map that takes a point and it just maps it to the point repeated twice. And this one is being mapped to the point repeated twice. And of course, when I write x0, I'm being sloppy. I really mean the homology class of x0 with respect to this group and the homology class of x0 with respect to that group. So now, because these are different, and this is an injection map, these are different. So these are homologically different. Now, if they're homologically different, it means that either these two components are different or these two components are different, right? Either these are different or those are different. So without loss of generality, let's say that the first components are different. So let's say without loss of generality, say that x0 is not equivalent to x1 in this homology group. It could happen, by the way, that they are both homologically different in this one and in that one, but in at least one of them, right? So we're in at least one of them. So we're picking, let's say, A prime. So in this one, they're homologically different. What does that mean? I.e., there is no path from x0 to x1 in S2 take away A prime. Okay, and now repeat the argument again. What do we mean? Well, the idea is that the original A was the image of this homeomorphism, and A prime was half of that interval. So we assumed it was the left half, but it could have been the right half. But the point is, this is again a Jordan arc. That's again a Jordan arc. So you can do the whole process again. You can cut this again into halves. So you're going to pick either the left half or the right half. And then you do it again and you do it again and again. So basically, so let's just summarize what we're saying. So this is a summary. So to summarize, if S2 take away A is not path connected, we can find 2 points, x0 and x1, so that two points and a sequence, maybe an A containing A1, containing A2, containing A3, containing, so that if you do S2 take away AN, you keep on cutting the interval in half, right? You're mapping 0, 1 homeomorphically to this arc A. And you said that if this is not path connected, you can cut the interval in half, pick one of the two halves, let's say the right one, that gives you A1, and then this way, and then you just reapply the argument using the same 2 points, right? There's no path between x0 and x1 that avoids that arc. So you cut that one, and you just keep on cutting it in half. So you can produce this nested collection of arcs that are getting smaller, so that on every level does not have a path, does not have a path from x0 to x1. And now the idea is, now observe that if you intersect all of these arcs, this is just they're going to intersect in a single point, because that's what you call the nested interval theorem. So that's going to be a single point. I'm going to call this point Q because it could be different from the point that we had in the beginning. They intersect in a single point Q. So this is some point, yeah, they intersect in some single point Q. Okay, and here's the problem. But there is a path, let's call it F, from F0 into S2, take away that single point with f of 0 is x0 and f of 1 is equal to x1. So here we're just using a very simple fact that if you have a single puncture on the sphere, it's connected. So we have this result. So there is a path. But what happens from here? So basically we're saying here's a point Q, here's x0, here's x1, and there's a path between those that avoids the point, points to point Q. So here's what you do next. You're going to pick a disk D, so maybe I should not say a disk because this is technically on the sphere. We're working on the sphere. So maybe I should say pick an open set. This is an open set on the sphere with Q in the open set and the open set not intersecting that path. Okay, you can pick some open set over here, and it does not intersect the image of the path. This is some point set topology. I'm sure you know how to do that. This is a compact set. This is a compact set. Q is not on the compact set, and they're both contained in S2, which is a Hausdorff space. And then there's like this really well-known result from point set topology that says you can separate a point from a compact set, things like that. I mean, basically, just a very quick outline, because you have a Hausdorff space. Well, you do not even need the fact that it's Hausdorff, but basically, for every, you can draw a disk. Well, yeah, you can draw an open set. So for every point on the curve, you can draw an open set that does not contain that point. And then, well, actually, I guess you do need compactness, but I really do not want to go there. I'm sure we know that would just be a waste of time. I should have probably not even brought it up. I think that should be the rule of algebraic topology. Never bring up any mention of point set topology. Otherwise, you take this very long 30-minute detour and you focus on less important things. Right? So you just find an O that does not intersect it. And here's the point. Because these intervals are shrinking, right? These intervals in the limit are shrinking down to Q. That means you can choose. Now you just simply choose n large enough so that an will be contained in O. Right? You can choose, there's like an an that stays within that O. But here's the problem. But then we constructed a path in S2 take away an, right? You can see that this path stays in the complement of an, which connects x0 and x1. And this is a contradiction because we said there was no path, right? We said on every level, regardless of what an you pick, there is no such path. So that is the proof of the lemma. So it's an interesting proof. It uses topology analysis. It's analysis. This is the nested interval theorem. It uses topology analysis and it uses algebraic topology, Meyer-Vittori sequence to make this work out. So that is the proof of the lemma. And with this lemma, we can now move on and discuss how you prove the Jordan closed curve theorem. So now let's say the theorem that we're going to prove. So if C in S2 is a Jordan curve, then S2 take away C has two path components. And we'll prove it in a very similar way. We're going to calculate the zero-dimensional homology of that set and show that it's z squared. So let's now write down what the proof is. So proof. So just like before, we're going to let f from S1 to S2 be a homeomorphism that takes S1 homeomorphically to the Jordan curve. And what we can do is we can set A to be the image of the left arc of the circle. Right, you have a circle that's like the left half of the circle, and F and B is the right half of the circle. By the way, these are Jordan arcs, okay? And F is a homeomorphism. So A and B are going to be Jordan arcs. So A and B, these are going to be subsets of S2, and these are Jordan arcs. And let's say that they intersect. So if you do A intersect B, that's going to be, they're going to intersect in exactly 2 points. So that's where these two arcs intersect. That's going to be F of a half and F, I'm sorry, that makes no sense, right? This is not an interval, so maybe what I'll just say is that, well, I'll just call those 2 points P and Q. How about that? So this is something on S2. These are points on S2. So we'll just do that. And then we're going to write for U, that's going to be the complement of this Jordan arc, and V is going to be the complement of the other Jordan arc. So their union would be S2 take away those 2 points, and their intersection is going to be S2 take away the Jordan curve C. So it feels very similar to what we did with the previous one, but this one's going to be trickier, and there's going to be an interesting complication that's going to arise as we do it. So now we use the Meyer-Vittoris sequence. So we will have H0 of S2 take away C. So that is the intersection. That gets mapped to H0 of U, and U is S2 take away A. Direct sum at H0 S2 take away B, and that gets mapped to the union of U and V. And the union of U and V is this. So that would be H0 of S2 take away P and Q. And then at the end, that gets mapped to 0, because that is the end of the Meyer-Vittoris sequence at the very end. And then we have, over here, we also have H1. So we have H1. Now, the lowering of dimension map, that's going to be on the intersection. No, that's going to be on the union. So here we have H1 S2 take away PQ. And let's start filling in this exact sequence. This is the one that we're interested in. We do know that when you do S2 two punctures, that homotopes to a circle. So this is the first homology of the circle. So we know that this is Z, isomorphic to Z. This one, this is the lemma. So this is where we use the lemma, that when you have, these are arcs, these are Jordan arcs. So the complement of a Jordan arc in the sphere is connected. So H0 is isomorphic to Z, and this is isomorphic to Z. So this whole thing can therefore be replaced by Z squared. This one that we have here, this is S2 with 2 punctures, and that's, again, as we said, that's homotopy. Well, it's just connected, so this is just going to be Z again. So now we get to the part that is somewhat interesting. Like, let's say what we want to show. We're saying it has 2 path components. So that should mean that if you calculate the zero-dimensional homology, this should be z squared. And we have this exact sequence. So we would like this map to be an isomorphism. That's what we want. If we can achieve that isomorphism, then we win. We have shown that this is isomorphic to z squared. Now, here is where the problem occurs. What's the image? So you want to show the image is z squared. The image is z squared. The problem is you do not really know anything about this map. So what's the image of this? Image, you can talk about, let's say, the kernel of this. The kernel of this is the image of that, but you don't really know anything about the image. Is the image 0? Like, how do you know that? And then you want to show it's surjective. So to show it's surjective, you would have to argue, you want to show this is surjective. So you have to show that this is the 0 map. Because if this is the 0 map, then the kernel is everything. Oh, no, that does not make sense. If I want to show that this is surjective, I want to show the image is everything. So then the kernel, oh, no, that's right. And then the kernel should be, so then I have to show that's the 0 map. So it's a bit unclear how to do it. I mean, you can try doing it, but the problem is we do not really have much information about the sequence to conclude what we want to. So this is going to be a good opportunity to introduce, so this is going to be a good opportunity to introduce something called cohomology. We've been mentioning this a number of times, so you probably wondered exactly what that is. And there is a way to make the proof work. So the way it's done in Breton, now Breton, of course, does it much more complicated. He does it in much more general. Breton proves what he calls the generalized closed curve theorem. But Breton uses something called reduced homology, which is actually not that difficult to explain what that is, but I'd rather not go there. I wanted to specifically show you how you make this a cohomological proof, because we'll be talking about cohomology anyway, and this is just a good time in the course to introduce it. So let's basically say what cohomology is without defining it for the time being. And then when we define it, you'll be able to fill in those gaps. So when we talk about homology of X, here X, this is going to be a space, a topological space. It could be any topological space. And this is supposed to represent basically n cycles. This is the group that you get out of those n cycles, of course with some identifications, but it's basically n cycles in X. Cohomology is written with a superscript. And here the distinction is going to be that X is no longer an arbitrary space, but it's going to be a manifold, a special type of topological space, actually a smooth manifold, which we will define in the course. But in topology, most spaces are smooth manifolds anyway, so it's not too limiting of an assumption. And the n over here, so what is, this is no longer cycles, this is going to be something else. So these are actually going to be n forms in X. What is a form? We're talking about differential forms. So we'll define all of that. So it's different. It's cycles, those are forms, but it will be defined. And the other difference in cohomology is homology is going down. It keeps on lowering dimensions. Cohomology, it goes up. Oh, and another thing I should say, this is the other important thing. This is an abelian group. Whereas n forms, this would be a vector space. Vector space over the real numbers. So that's the other distinction. So now what is interesting about cohomology is, so let me say this. Cohomology loses information. In other words, if you know homology of X, so assume X is a smooth manifold, then you can instantly find its cohomology. So homology carries more information, right? There's more here, and there's less here. And going from this one to the other one, this is what is known as the Theorem theorem, which we will all make that explicit. From going from homology to cohomology. However, you're not able to reverse the process. If you know the cohomology of a manifold, that does not necessarily make it possible for you to go back. So there's more information in homology. So based on that, the immediate question to ask is, why should we care about cohomology? Other than the fact that it sounds cool and fancy and all of that, like why should we care about cohomology? And the answer is because it is simpler to use. And the analogy I like to say is, so this is like the analogy, is that in analysis, complicated sums and integrals are often estimated, right? We do that all the time. If we want to show that some kind of sum converges, it might be very hard to work with the sum directly. It has way too much information in it. And if we can estimate that sum from above or below, often if the estimate is somewhat good, we're losing information. It's no longer as accurate as the sum itself, but it is just enough to show what we want, and it is easier to use. And that is exactly what cohomology does. Sometimes working with the homology could be a lot harder. Like for instance, this is a perfect example of this. If you try to show that, you're going to see that it's not clear why this is an isomorphism. You can try to think this through. We do not know anything about this map. We do not, well, maybe you could say something about this map, but we do not know anything about that map. Because in order to understand this map, in a way, you have to understand what that is itself. So, and that's why it's hard. And there is a way, like I said, there is a way to do this using homology, but you have to use something called reduced homology, and that's what is being done in Brennan. I want to deliberately avoid doing that because I do not want to introduce extra terminology in this class if it's not necessary, and also because we're going to be talking about cohomology anyway, so let's do it the cohomological way. So here's the way this is going to go. That this is our sequence. Okay, this is going to be our sequence. So you're going to see how this is a lot easier. So let's remove all of this, and let's just focus on the sequence. The goal is we want to show this is z squared. Okay, let's forget about all of this. This is what we have. We have z going to something, right? A mysterious group goes into z squared, goes into z, goes into 0. Okay, we have this. So this is the setup that we have. Now, when we use cohomology, we have the exact same sequence. The distinction would be is that instead of subscripts, we're going to have superscripts. So you're going to have 1 over here, 0 over here, 0 over here, 0 over here. The other distinction would be is that the arrows would go in the other direction. So instead of going down, they will go up. Like this. The arrows will go up. So the arrows are ascending. The arrows will go up. Now, by the way, these are all manifolds. S2 is a manifold. This is a manifold. S2 take away 2 points is a manifold. You might be concerned, and you might say, if you're saying it's a smooth manifold, are you not assuming that the homeomorphism to C is smooth? No, because this is just an open subset of a smooth manifold. So it's going to be smooth. I mean, you're going to see when we talk about manifolds, all of these are smooth manifolds. They're topological spaces, but they're also smooth manifolds. So that's why you can calculate their cohomology. And now, the other distinction is that these are vector spaces. So instead of having Z, you're going to have R. That's the other distinction. So what we'll do is, and if what I'm saying bothers you, that's the point of the course, to unbother you when we get to the stuff on manifolds and cohomology. And then you'll see how it comes together. So you're going to have that this is R, this is, and then you have the mysterious vector space that we're trying to understand. We want to show it's R squared. This is going to be R squared. this is going to be R, and this is going to be 0, like this. And these maps, maybe we can give these names. Let's call this map, for lack of a better name, let's call this one A, let's call this B, let's call this C. This map, this is just the 0 map. So we give these maps name, and these maps are going to be linear maps. Linear maps. And we're going to use a theorem from linear algebra. So now we reduce everything back to linear algebra. And basically the idea here is, I'll just say it like this. Linear algebra is easier than group theory. And not just group theory, but abelian, even abelian group theory. So to give an example, so there's many ways. So for instance, so here's an example. If there's an injection from Z to itself, it is not necessarily an isomorphism of groups. It does not have to be. So for instance, just multiply by 2. That's a homomorphism of groups, but it's not an isomorphism. But if you inject the real R into R, then it is an isomorphism. Because if you multiply by 2, you can reverse it, because you can divide by 2 among the real numbers. So it's an isomorphism. So this is just one of the ways that it's simpler. Another way that this is simpler is, because you're dealing with vector spaces, there's not many options that you can put here. Is this 0? Is this the 0 space? Is this R? Is this R squared? Is this R cubed? Is this R to the 4th? Because vector spaces, they're just isomorphic to a certain number of copies of R. You might be skeptical and you might say, how do you know it's a finite number of R? As you will see, it has to do with the fact that these are finite. But if these are groups, then anything goes. I mean, if this was Z and this is Z squared, you could have Z mod 3 over there. You could have Z mod 3 direct sum Z mod 2. Like with groups, it's a lot more complicated, but with vector spaces, the possibilities just narrow down greatly. So it is true you are losing information, but you're still retaining just enough information to be able to complete the proof. You retain the relevant information to complete the proof. But if you're using homology, you're focusing on this additional information that is not necessary for you to complete the proof. And it makes it harder when you're using homology. OK, so now that we have this, what are we going to do? So we're going to use the following theorem from linear algebra. And it goes by the name rank nullity theorem. Rank nullity theorem. So here's what the theorem says. It says that if f from V to W is a linear map between vector spaces, these are real vector spaces. It doesn't, they do not have to be real vector spaces, but for what we're doing, they're real vector spaces. And if the rank of f is n, and the nullity of f is m. Now, if you do not know what the rank is quite simply, this is the dimension of the image of f. Okay, so you take the image of f, you get a subspace, and it's the dimension of that subspace. And nullity is what the kernel, that's the dimension of the kernel of f. Now, maybe in your introductory linear algebra class, the way they taught you about rank and nullity is with a matrix and looking at pivots and counting them. But this is like a more sophisticated version. It really is the same thing, because the way you would calculate the rank and nullity is by row reducing the matrix that represents the linear map. But anyway, this is what you have. So if the rank is n and the nullity is m, so then the dimension of your vector space is n plus m. So in particular, V is a finite dimensional vector space, and it's the sum of these two numbers, assuming these are finite numbers. How do you prove this? Well, the proof of this is really what you call the fundamental isomorphism theorem, because the fact that you have a linear map, it would mean that V mod the kernel of f is isomorphic with the image of f. So now the image of f, that's isomorphic to r to the n, right? R to the n, and the kernel of f nullity that's isomorphic to R to the m. And when you take the quotient of a vector space by another vector space, you're subtracting the dimension. So this would be R dimension of V minus m. Okay, so in particular, V is finite dimensional, and its dimension is the sum of n and m. That's basically the way you prove it. So rank nullity theorem. So we're going to use the rank nullity theorem to do this. So let's remove it. It's just going to get in the way. So let's start with this. So now this, the image of this is the kernel of that. So the nullity of C is 0. That would mean that the rank of C has to be 1. The reason by the rank nullity theorem, these together have to add up to this dimension from the C map. Then from the exact sequence, we have that the nullity of B has to be equal to 1. From here, it follows that the rank of B also has to be 1, because rank and nullity of B has to add up to this dimension. Therefore, the nullity of A has to also be equal to 1. What about the rank of A? Now this is a bit tricky, because previously the way we get the rank is we just see what this number is, but we do not know what the correct dimension here is supposed to be. But the way we can figure this out is by observing that the rank of A, whatever it is being mapped into R, is being mapped into the reals. So the rank, it's a subspace of R, and there's two possible subspaces of R, either the 0 subspace or R itself. So the dimension of the subspace is 0 or 1. So we do not know what it is, but it is either 0 or 1. Now, I would like you to realize that if it is 1, then the proof is complete, because then the rank and nullity of A are both 1, and then they add up to R, and they add up to 2. So we get R squared, and then the proof is finished. That's what we wanted to show. We have two components. But we now consider the other possibility. The other possibility is, what if it's 0? Okay, what if it's equal to 0? If the rank is equal to 0, then this would mean this has to be the real. It has to be the reals. And we argue that this just leads to a contradiction, that this is impossible. So why does this one lead to a contradiction? Well, rank is 0, okay? So that means this is the 0 map. Now, unfortunately, and this is the unsatisfying part, is that if the rank is 0, and that is R, and not R squared, I believe this is completely consistent with this exact sequence. So we almost got the proof. We wanted to show that it has two components, and we're getting that it's either Z squared or it's Z. And we want to get this one, but the question is, how do you rule that one out? So if that bothers you, you just have to wait, because you see, we're not actually, like, we try to do it with the exact sequence alone, but sometimes you have to actually interpret what the map says. And we're going to talk later on about this cohomology and what these maps are. And the mapping that takes you from, that increases the degree on homology, is basically the derivative. We'll make this precise. And you're essentially asking, this is oversimplified, can the derivative operator be 0? And the answer is no, because you have functions that are not constants, right? Because when does the derivative become 0? When you have a constant function. Well, you have functions other than constant functions on this. So you just take any function that's not constant, its derivative is not going to be 0. And that's like a overly simplistic explanation why this cannot possibly be the 0 map. So it seems you actually have to consider this mapping and realize why it's a nonsensical type of a map. So I guess we almost got to the proof of the Jordan closed curve theorem, but there's that small issue. But it will be fixed when we get to cohomology anyway. If this bothers you, you can just look at Breden's proof that uses reduced homology instead.